Okay, so hello and welcome back. So in this video we want to talk about the continuous frequency distribution, and what we will do basically using the continuous frequency distribution, we will then continue the mean deviation about mean and the mean deviation about median in the case of the data that has been basically in the case of the kind of data that has been arranged or organized in the form of continuous frequency distribution. So continuous frequency distribution means that, for example, in the previous cases, what we had was that we had, for example, we had our x of i's. So suppose that, for example, we had our x of i's in this form. We had basically, let's say that this is x of I and this is f of I. So you have, for example, 3, 6, 9, 12, 13, 15, 21, 22, right? So we have these x of i's, and then we have the frequency related to these are 3, 4, this is just an example, 5, 2, 4, 5, 4, 3, 4, 5, 4, 3. So what this means is that the data that the observations that you had, for example, let's say that this is the ages of, for example, 12, 14, 18, 23, 27, and 30. So let's say that this is the ages of 30 people, and each of them you would call an observation. You have 30 observations, and each of those observations is the age of a person, for example. Meaning that you have 30 people in front of you, and you go up to them individually, each and every one of them, and ask their ages. The first one tells you that their age is 3. The second one tells you that their age is 3. The third one tells you that their age is 3. The fourth one tells you that their age is, for example, 6, and another 6, and another 6, and another 6, 4 6s. You have 3 3s. And then you have 5 9s. So you have 9 9 9 9 9. And so on and so forth. And in the same manner, you got basically 30 such numbers. And of course, it doesn't necessarily have to be basically that, it doesn't necessarily have to be in such a way that the 3 first people necessarily are basically 3 years old. That it could be that, for example, you got this 3 from the first person, and this 3 you got it from the 10th person, and this 3 you got it from the 15th person. But then when you rearrange your numbers, rearrange your numbers in, for example, in ascending order, then your data or your observations will be represented in this ascending order. And in the same manner, you get basically basically all of these 3 observations, meaning that you are, observing their age, and each of those numbers represents or is called an observation, or technically called basically an x of I in the language of statistics. It's called an x of I, and then f of I is the frequency related to each of those observations. Meaning that the frequency related to this observation 3 is 3, meaning that the number 3 has been repeated throughout all of your observations 3 times, or 6 has been repeated throughout all of your observations 4 times, and so on and so forth. So then what happens is that that's basically this kind of representation, and then you can put all of your observations in a table. And I think I'm not really sure about this, but I think, let me see if there is a name over here. So this is called a discrete frequency distribution table. Discrete frequency distribution table, right? So this is called the discrete frequency distribution table. Now the name is a big name, but it doesn't need to be intimidating or anything. All that it means is that basically you have your basically all the distinct observations you have written them down individually. And then you have counted how many times each of them has occurred, and then that how many times each of them has occurred has become the frequency of each of those observations. And so you have basically written down their frequency, and each individual distinct observation you have written down, and that is called the discrete frequency distribution table. Now there are times when this is not going to work for you, meaning that depending on the nature of the data that you have collected, you cannot represent your data in the form of a discrete frequency distribution table. What that means is that, for example, you get for example a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10, and an 11, a 12, a 13, a 14, a 15, and so on and so forth, going all the way up to 1,000, right? For example, all the way up to 1,000. And then again you will get another 1, you will get another 3, you will get another 5, you will get another 7, you will get another 12, you will get another 15, you will get another 18, all the way again up to 1,000. Well, this time randomly, just picking a couple of numbers from here and there. And now this data, if I want to represent this data in the form of a discrete frequency distribution table, what happens is that I would need a table whose length is basically 1,000 individual numbers. So I would have to write 1, 2, 3, 4, 5. I would have to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 1,000, which is something which is not practical. So what I need to do is that I need to group them together, because otherwise I would not be able to represent them in any sort of table. My table would need, for example, 1,000 entries. So in such cases, what I need to do is that I put all of these numbers, for example, supposing that I have, for example, all the way up to all the numbers starting from 1 all the way up to 1,000. So one thing that I could do is that I could, for example, put all of these numbers together and call it, for example, 1 to 10. And I could call it 1 to 10. Or basically I could call it, for example, 0 to 10. And then, for example, these numbers all the way up to 20, for example, I can call it, for example, 10 to 20. And all the numbers from, for example, from 21 to 30, I can call them, for example, 20 to 30, and so on and so forth. And so I will get all of these groups, 0 to 10, 10 to 20, 20 to 30, and so on and so forth, and I would get basically 100 such groups, right? 100 times 10 would be each group is contains 10 numbers. 100 times 10 is equal to 1000. So then I would get 100 such groups. Still, it would not be manageable. So I would still go for example, 0 to 100, for example, and then 100 to 200, and 200 to 300, and so on and so forth. So then what I can do is that I can create such a table, essentially the same type of table, and then I can write, for example, I don't know, if this is, for example, the heights of people, so then over here I can write the heights, for example, in centimeters, in meters, or whatever that was. And then over here I can write the number of people. And then you need to count. For example, basically from 0 to 100, you had, for example, basically 0 to 100, and then 0 to 100, and then in that case you had, for example, 20 people. Then you had, for example, 100 to 200, you had, for example, 25 people, and so on and so forth. So this kind of managing your data, and this way of managing your data, or essentially this table, is called the continuous frequency distribution table. It's called the continuous frequency distribution table. So a continuous frequency distribution table, meaning that the word continuous, well, most probably is referring to the fact that basically your frequency is continuous, meaning that, or basically these are called classes. So these classes are continuous, are joined together, meaning that there is no gap here between the classes. You go from 0 to 100, and then 100 to 200, 200 to 300, and so on and so forth. So it's called the continuous frequency distribution table. Now, as you can see, basically once you create this table based on your data, and then you want to do something on your data, the problem here is that you have lost much of the information about individual heights. For example, you have no idea, for example, there is no way to figure out exactly, for example, what was going on with the height, for example, I don't know, 76.5 centimeters. This height is just not there anymore. You just have some sort of number, some number that represents all the heights that have fallen into this category, for example, 0 to 100. So in this kind of table, since the number of your observations was way too high, then of course you had to lose a whole lot of detail, but otherwise you would not have been able to put your data in the form of a table. And if you do not do so, of course statistics is impossible. And statistics being impossible, meaning that you cannot actually get any sort of information from your data unless you did it manually, just adding numbers together, basically done strictly by a human being. But when you do it this way, then this kind of work can be given to a machine, and a machine can basically do it for you. Otherwise, it's a tedious work. You have to just keep counting how many ones do I have, how many fives do I have, and then add them together, divide, multiply. So it's not really possible when the volume of your data becomes a little bit over, for example, 10, 20, 30 numbers. So that's basically called the continuous frequency distribution table. Now, as you can see, when you come over here, the discrete frequency distribution table, in this case, what you have is that you know exactly that this observation 3 has occurred 3 times. That is, basically, if this 3, for example, represents, 3 hours, for example, or if this 3 represents, for example, 3 amps or 3 volts or whatever that might be, you know that observation has occurred 3 times throughout your observations, and you have a whole lot of detail when it comes to discrete frequency distribution table. But again, you can do this sort of thing when there is when the number of the distinct observations is not too high, meaning that, of course, the number of your observations could be too high. You could have, for example, 1,000 different observations, but distinctly their number has to be low. For example, that you need to have only 3s, you need to have only 6s, only 9s, only 12s, 13, 15, 21, 22. And of course you can have 1,000 of these 20 of this 21. You could have 5,000 15s, you could have 5 million 13s, you could have 12 million, for example, 12s. You could have 15 million, for example, 9s. That's not a problem. That would be just a frequency. But then if you have 12, 12.5, 12.3, 12.2, 12.8, 12.7, and all of those individual numbers, then you would have, for example, 1 million, for example, distinct observations. And then suppose that you had, for example, 1,000 such numbers, and you were to fit it in a table like this, then the length of this row of the table would be probably 2 kilometers or 2 miles or something like that. So that's not possible. So that's basically why we use the continuous frequency distribution table in the first place. And then, of course, if I see an example, I can tell you, for example, how to do certain things when it comes to discrete frequency distribution table, or when it comes to continuous frequency distribution table. But I don't remember them off the top of my head, I don't remember them because I have forgotten them. And but basically, then when it comes to when you rearrange your data in a continuous frequency distribution table, then the rules change a little bit. You have to do things a little bit differently in order to get essentially the same kind of results, for example, from your data. We will get to them. So that's basically, first of all, what a continuous frequency distribution table is and why you need it in the first place. So then basically, so here it says that a continuous frequency distribution is a series in which the data are classified into different class intervals. So each of these is called a class interval. A class interval. So each of these is called a class interval. And so it says that the continuous frequency distribution is a series in which the data are classified into different class intervals without gaps along with their respective frequencies. So there is no gaps here, and the frequency of those class intervals will be basically a part of your continuous frequency distribution. Now, for example, the marks obtained by 100 students are presented in a continuous frequency distribution as follows. So this is the mark of 100 students. The marks of 100 students. So suppose that you have, for example, over here you have the marks obtained, and here you have the number of students. So here you have the marks obtained, and here you have the number of students. So the way that you work with, basically you arrange your data in this kind of representation. You say that, for example, if your marks fall within this class interval, then of course you would include it in this frequency, or the number of students, which happens to be 12 in this case. And then if it falls within this class interval or this category, you will simply write it over here. If it falls within this category, you will write it over here. If it falls within this category, 30 to 40, you will write it over here, 20 for example, and so on and so forth. And then you have, for example, 50 to 60, which is, for example, 6. Okay, so now let's first go about basically calculating the mean deviation about mean, for example. So to calculate the mean deviation, for example, the mean deviation about mean, so while calculating the mean of the continuous frequency distribution, we had made the assumption that the frequency in each class, while calculating the mean of a continuous frequency distribution, we had made the assumption that the frequency in each class is centered at its midpoint. And if this makes no sense to you, of course you would be what I mean to say is that you see, the problem with this continuous frequency distribution is that, as I mentioned, once you rearrange your data in this way, you will lose a whole lot of basically a whole lot of detail, and so then it's not easy to decide what is what once you lose your data and then get all of your data in the form of these class intervals. For example, if you come over here to this table over here, if you have this kind of, for example, this kind of table, this is a discrete frequency distribution table. So in this table, everything is actually everything is laid out, and you know every sort of information about every sort of observation, every sort of individual distinct observation you might have collected during the data collection process, right? So then here you don't have to make any assumptions, because all of the data that you had is already at your disposal. But then when it comes to this kind of the basically continuous frequency distribution table, then what happens is that you basically what this class interval represents is that all that you know about this class interval and the frequency of that, for example, in this case is 12. All that you can say about this class interval and the related frequency is that there have been 12 numbers. There have been 12 numbers in such a way that those numbers started from 10 and, for example, ended in 10. Of course, technically what I'm saying is not absolutely correct, meaning that you have to basically start from, I suppose, if I'm not mistaken, for example, if you have a 10, you see that this class interval goes from 0 to 10. This class interval starts from a 10 and goes all the way up to 20, and this is supposed to be a 20. So this goes all the way up to a 20. So that means that if you had a 10, would you put it in this class interval, or would you put it in this category, or in this category over here? So as a matter of convention and agreement, the way that everything has been developed in statistics is that if you have a 10, that 10 goes into that 10 goes into this category here, as far as I can remember. That 10 goes into this category, and then this goes from, I suppose, 0 to 9. And then again, for example, 20 goes into this and not this. 30 goes into this and not this, and so on and so forth. So for example, about this class interval, all that you can say is that there were 12 such numbers in such a way that those numbers, let's say, assuming that what I said was just right, so you can say that there were 12 numbers such that basically those numbers have been between, or those observations, the value of those observations has been between for example, 0 and 9. But there is no way to know what those observations were. You have no idea what those observations were, whether they were a 0 or a 1 or a 2, or, for example, a 5. There is no way to know. So then when you want to, for example, find the mean of all of this data, suppose that you want to find the mean of all of this data. So you don't have your basically your observations are practically lost. There is nothing that you can know about this. So and so you have to make some assumptions, and these assumptions of course get you very close to the actual values if you hadn't put your data, basically if you hadn't put everything together, and if you hadn't put everything into these categories, meaning that if you had kept everything in their own, for example, if you had kept every distinct observation, for example, in this format, meaning that if you had access to each and every distinct individual observation. So those assumptions that you make get you very close to, well, I would say, I don't know in terms of percentage, I cannot say that because I've never actually calculated that, but they get you reasonably very close to the actual value of any sort of typical calculation or operation that you might do on your data if you basically arrange your data in the form of a continuous frequency distribution table in this format, basically. Now, one of these assumptions that we made in the, well, of course, I suppose it was in the previous in class 10, I suppose it was. So one of these assumptions that we made when we wanted to calculate the mean of the continuous frequency distribution, so when you want to calculate the mean, we had the assumption that the frequency in each class is centered at its midpoint, meaning that now I don't even understand what I'm saying, meaning that I don't remember what that actually exactly was, but let's read on, see what that was. So, meaning that I suppose it says that while calculating the mean of a continuous frequency distribution, we had made the assumption that the frequency in each class is centered at its midpoint. Okay? Meaning that the frequency 12 is centered at the midpoint of the class, meaning 5, for example, something like that. But let's see what that means exactly. Now here also we write the midpoint of each given class and proceed further as for a discrete frequency distribution to find the mean deviation. Now let us take the following example. Now let's go through this example and let's see how we calculate the mean of a set of data if we have our data in the form of continuous class intervals. Okay, so now let's work through this example. If you don't get to the point, meaning that using these class intervals and everything, things are a little bit different, meaning that you have to know all the exact agreements that there are in statistics related to these tables. And so if you don't get the point, then we will go back and probably do a couple of examples how to calculate the mean, the median, and the other thing related to a set of observations arranged in continuous frequency distribution in continuous frequency distribution. So now example number 6 is find the mean deviation about the mean for the following data. So suppose that you have your marks, basically we have some, basically let's say that this is the marks obtained. You have the marks obtained, and here you have the number of students. So this is basically the frequency. related to each class interval. This is called the class interval. This is the frequency of that class interval. And then there is something called the midpoint of each class interval, which is actually taken as our x of I in this kind of continuous distribution, in continuous basically frequency distribution. We take the average of the class interval and call it x of I, because there is no way to know where your x of i's are in a class interval. For example, when you say 0 to 10, for example, then you have 10 to 20, then you have 20 to 30, and so on and so forth. Of course, as we mentioned before, there is no way to know where exactly your individual basically observations fall within this category, so we have to make some assumptions. We make the assumption that the x of I related to this class interval falls exactly between, is the average of the lower limit of the class interval and the upper limit of the class interval. And that means that, for example, 10 minus 0 divided by 10 is equal to 5. I call this, for example, 5. I call this, for example, 15. I call this, for example, 25, and so on and so forth. And then that's it basically. So now suppose that your marks obtained fall within these class intervals, meaning that you have 10 to 20, you have 20 to 30, you have 30 to 40, you have 40 to 50, you have 50 to 60, you have 60 to 70, you have 70 to 80, and that's it. Now the frequencies related to these class intervals are 2, so these are the number of students, or f of I is 2, 3, 8, is 2, 3, 8, 14, 8, 3, and 2. 8, 3, and 2. And then and then we have the midpoint of these class intervals, where you get basically 5, you get 25, you get 35, you get 45, you get 55, you get 130. So 130 divided by 2 is equal to 65, and 150, so that's 75. So that's the midpoint, or basically simply x of I. Now you can simply calculate f of I times x of I. So f of I times x of I you can calculate by multiplying these two columns together, meaning that 2 times 5 is equal to 10, 3 times 25 is equal to 75, 8 times 35 is equal to 240, 280, and 14 times 45 is 10 times 45 is equal to 450, and 4 times 40 is equal to 160, and 4 times 5 is equal to 20, so you have 0, and 11, 13, 1, and you have a 630 here. You have 8 times 55, 8 times 50 is equal to 400, 8 times 5 is equal to 40, so that's 440. 3 times 65 is 180, and 195, and 2 times 75 is equal to 150. The next thing that we have, basically you want to, of course I'm calculating all of this because I'm calculating the mean deviation about the mean, meaning that first I need to calculate the mean, which is nothing but basically x bar. We said that it's equal to 1 over n over sigma. So the x bar is basically x of I times f of I, sigma x of I times f of I, divided by n as I goes from 1 to n. So here I need the sigma x of I f of I over here. So I need to calculate this. And also once you calculate that, then the mean deviation about the mean is going to be equal to 1 over n sigma basically f of I times the absolute value of x of I minus x bar as I goes from 1 to n, right? So these are the two formulas that you have. So depending on these formulas, of course, based on these formulas, you need x of I times f of I, which we have, or f of I times x of I, which we have already calculated. And then we need to take the calculate the sigma of that. So let's do that here, and then we will see about the rest of the things. So then you can write sigma x of or f of I times x of I as I goes from 1 to n is equal to basically all of these numbers added together. That's 85 plus 280, 85 plus 200 plus 280 plus 630 plus 440 plus 195 plus 150. So that's equal to 5 plus 12 is equal to 10, 1, so 16, 17, 20, 20 plus 13 is 33, 33 plus 5 is 38. I have a 3 here. 5 plus 6 is equal to 11, 11 plus 6 is equal to 17, that's 1780. That is 1780. It seems that I made a mistake. Two times. Oh, that's a 15. Okay. That's a 15. And then I added 10 over here. 15, 25, 35, 45, 55, 65, 75, and 1790, it's supposed to be 1800. So let's do this again. So you have a 10 and 75 is 85, and then you have 280. You have 630, you have 440, you have 195, and you have 150. So you have a 0 over here, 1, and 16, 17, 20, 20 plus 13 is equal to 33, 38, and you have a 3 over here, 11 plus 4 is equal to 15, and I don't understand. So 10 plus 70 plus 75 plus 280 plus 630 plus 440 plus 195 plus 150 is 1780. My calculation is not incorrect. 30, 75, 280 630, 440, 195, and 150. That is, oh, okay. I'm sorry. This is supposed to be 2 times 15, which is equal to 30. I should have actually. Okay, so then sigma f of I x of I is equal to 1800. Is equal to 1800. And so that's basically what we need for here. Now, the next thing that we need here is x sub I minus x bar, and take the absolute value of that. So I write the absolute value of x sub I minus x bar, and that is equal to basically x sub I is here and x bar is here. So 1800, for example, 15 minus 1800 is the same thing as 1785. Oh, I haven't calculated x bar yet. Okay. So then based on this, my x bar is going to be equal to 1 over n, and 1 over basically n is, of course, as you know, is sigma f of I. So sigma f of I as I goes from 1 to n is equal to n, capital N, and that is equal to basically 2 plus 3 is equal to 5, 5 plus 8 is equal to 13, 13 plus 14 is equal to 27, 27 plus 8, 27, this is 27, 11, and plus 2, so you have 7 plus is equal to 10, 1, and then you have 4 over here, 40, right? So then what that means is that your x bar, or the mean, is equal to 1 over 40 times sigma f of I x sub I. Sigma f of I x sub I is equal to 1800. So that's 180 divided by 4, and 90 divided by 2, and 45 divided by 1. So that's equal to 45. So that is equal to 45. So your x bar is equal to 45. Now, x bar is equal to 45. Now, if you want to calculate x sub I minus x bar, 15 minus 45 is equal to 15 minus 45 is equal to what? Is equal to negative 30, negative 30. So that's a 30 over here. Then you have basically 25 minus 45, which is equal to negative 20, or 20. Basically, the absolute value of that would be 20. 35 minus 45 is equal to 10. 45 minus 45 is equal to 0. So 55 minus 45 is equal to 10. And then you have 6, 7, 45 is equal to 20. And then 7, 5 is equal to 30. And then you need to calculate f of I times the absolute value of x of I minus x bar. So you have f of I times the absolute value of x of I minus x bar, which is equal to basically, this is x of I minus x bar, the absolute value of that, times f of I, which is this number over here. So you have to multiply this column by this column. 2 times 30 is equal to 60. 3 times 20 is equal to 60. 8 times 10 is equal to 80. That is a 0, 80. Then you have 60. Then you have 60. And sigma f of I, sigma f of I times the absolute value of x of I minus x bar as I goes from 1 to n is equal to all of these numbers put together, which is equal to 120, 200, 200 plus 200 plus basically 120 plus 200 is equal to 400, is equal to 400. And then if you divide that by and then what that means is that the mean deviation about the mean is equal to 400 divided by n, which is equal to sigma f of I, which is equal to 40, which is equal to 40, which is basically 400 divided by 40 is equal to 10. So the mean deviation about the mean is 10. So that's how you solve this kind of problem. Now there is a part called the shortcut method for calculating mean deviation about the mean, and that is basically we can avoid the tedious calculations of computing x bar by following step deviation method. Recall that in this method we take an assumed mean which is in the middle or just close to it in the data. The deviations of the observations or midpoints of classes are taken from the assumed mean. This is nothing but the shifting of origin from 0 to the assumed mean on the number line as shown in this figure. So what that means is that, now let me read on to see the whole thing. So if there is a common factor for all the deviations, we divide them by this common factor to further simplify the deviations. These are known as step deviations. The process of taking step deviations is the change of scale on the number line as shown in this figure. And the deviations and step deviations reduce the size of the observations so that the computations, that is multiplication, etc., become simpler. Let the new variable be denoted by d of I as x of I minus a over h, where a is the assumed mean and h is the common factor. Then the mean x bar by step deviation method is x bar is equal to a plus basically sigma f of I d of I as I goes from 1 to n divided by n times h. Let us take the data of example number 6 and find the mean deviation by using step deviation method. So the step deviation method is a method to basically to further reduce the work of the volume of calculation that you normally do in order to calculate basically for example the mean of some numbers. And let me explain this to you. Okay, so now in order to basically understand all of those things that we just said, basically in order to understand, here we said that there was a shortcut method for calculating the mean deviation about the mean, and we said that we can avoid the tedious calculations of computing x bar by following step deviation. So there is something called the step deviation method. The step deviation method. And do we need to talk about this in order for us to be basically in order to be able to move on? And that goes into the previous chapters that we have done. So I will go and pick a couple of examples that represent this step deviation method properly, and then I will come back.